Welcome back to our statistics playlist here. We're going to talk about interpolation. Interpolation is one of those pieces that emerges from our spatial understandings, our understandings of near things being more similar than distance things, a little bit of math in here, and something that's a very common and powerful geospatial technique within GIS. Let's imagine, you have some point data. Love some point data. And with that point data, you might have readings at each of these points. Maybe these are temperature gauges, maybe these are crime incidences, maybe it's groundwater information, whatever it might be. Now, you might have this point data and say, wow, I'd really like to understand what is going on between the points, in the surfaces between. Certainly rainfall, temperature are good examples of things that do occur continuously across the Earth's surface, but we don't have, that dense grid from a couple of videos ago where every point is evenly spaced every 5 meters and everyone has a weather station and so on and so on and so on. So we might want to use some interpolation techniques to understand what's going on in the missing data in between. So we've got a little data set. It doesn't matter what it is. Our pink and purpley values are our high values, our orange and brute sienna values are our low values, greens and blues in between. We got data. There it is. Now, at its core, at its basis, interpolation is creating new information based on the inputs and the known relationships between other pieces of data. Much like when you connect the dots with a linear line, interpolation connects the dots, but multidimensionally across the spatial surface. So there are many points. We want to see how they're related to each other. We want to interpolate. It's a lot more complicated than just 2 points because we have a whole surface of points. Look at them all there. So we want to do our best to create and understand the best relationship between all of these points. Here are our sample datas again. So again, we could just draw a line between 2 of these points, but that misses the relationships that those 2 points have with all the other points. There's a lot going on when we do interpolation. Now, linear interpolation, just from point to point, works something like this. We have a value of 10. Maybe these are elevation values. 10 on the left, 20 on the far right. What's the value at the midpoint? Think to yourself. Say it out loud. Right, I'd say about 15. 10, 20, 15 in the middle. Great. What about that point right next to 20? In the far right. 10, 20, closer to 20, probably 19, 19 and a half. Something like that. The point on the far left, well, it's closer to 10 than it is to 20. It's not halfway to 20. Maybe 12, 11 and a half, something like that. So linear interpolation, we're estimating values based on the slope of the line, all those kind of things. If we get new data, well, now what's the value at this point? Well, we see there's a 30 in the way, so it's probably more like 21. Now this value is probably more like 20, right? Midway between 10 and 30. Think back to our sampling discussion. The more samples you have, the more continuous data set you have, the less you have to interpolate. Oh, but it's a lot of work. Maybe I'll just make my interpolations. The ever back and forth of spatial data sampling. How much time can you spend sampling? How much time can you spend working? How much time can you spend confirming data? How much time can you spend interpolating data? The interpolation toolboxes inside of ARC specifically are all in the spatial analyst tool set. We're going to look at a few of these just for sample reasons to see how they operate. And the reason we like to see these differences, there's the sample data again, if you've forgotten it, is because it's not just as straightforward as choosing one method and always using that method. Different methods lead themselves to different problems. It's also not choosing which method you like the most. It gives you the answer you want. But a lot of the work that we do is kind of locked in the underlying math and process. So nearest neighbor is a triangulation format. Much like the GPS system, we take a triangle of points, 3 of them, and then we calculate the values based on their relationship. Delaunay triangulation is another name for this. And you can imagine, just imagine triangles, just a network of triangles. Wait a second, it's a 10. It's kind of like a 10. Remember those? Except for irregular network results in a map, something like this. It's not, I guess we could make it 3-dimensional if we wanted to, but we haven't here. Nearest neighbor triangulation. We can see the relationships. We got kind of a weird thing in the top, right? Because we only have those 3 closest points aren't giving us a ton of maybe reasonable data. We can also see that our output is not square. Why do you think this output might not be square? Well, one of the reasons is because there's no data out there. We are triangulating, we're using real data, so we can't make any guesses beyond where our triangles can be run, where our triangles can be made. So if it's all triangles, we're going to end up with a lopsided output. Another option we have is inverse distance weighting, IDW. Again, the closer you are to something, more weight is given to a certain distance where we stop looking at data points. Now, this is Tobler's law in full function. The nearer you are to something, the more likely you are to be like that something. So the thing that is closest at 1 kilometer is given the most weight, and then it decreases from there. Very bullseye, as you can see from the response here. Now, we get a square out of it. We get a rectangular, I guess it's more square than rectangular, but we get a full shape out of this. There's not a bunch of missing data. But very bullseye, lots of hot spots, especially lower right. Then there are splines. Splines are fun to say, and are smooth curves that are fit through data points. But splines don't trust you. And I know it's just math, and math is emotionless and logical at the end of the day, but I don't like splines, and splines don't like me. What I mean, of course, is that splines treat your data as incomplete, as all interpolation methods do, right? They're all built up so that you can create surfaces from incomplete data points. But splines are especially not trustworthy that you have collected the maximums and minimums within your data set. So splines will predict maximums and minimums above and below the data that you have. That might be reasonable in some cases, but it might be very unreasonable in others. Say you have elevation data, and you know you surveyed the highest and lowest point in your data set. Well, Spline's just going to come along and say, nope, sure didn't. Maybe it's not appropriate there. But in other cases, maybe you're not confident you have the extreme values, and the Spline could help you maybe make an estimate, a reasonable, mathematically driven estimate about where on your surface, where in your spatial domain there might be higher or lower values. Spline has done something odd with our fake data set here, and that's filled in behind in this lower brown value. No idea what it's on about there. Finally, there are Crigings. Crigings are distance weighting with spatial correlation. So it's like an IDW, but it takes into account a spatial autocorrelation calculation. It has a better measure of error. It's a lot more powerful than the other tools. And it gives different results, which we can all see there. And apparently an ARC gives us results at a different spatial resolution as well, which is quite exciting. In each of these, this is a good, I like to think about this as elevation data, but it really doesn't matter what it is. We have this pink ridge down the middle of our data, and we have two depressions in that brown and orange, lower left and top right. We have a gradient between them. That's what we got. Our peakiest values, our highest values are those pink/white values, lower right. They are standing out the most. And truly the pattern is about the same between all of them. The details are different, but the pattern matches. Interpolations allow us to fill in these gaps and to understand what is happening between what's known. And if we trust and understand and operate with a good sense of spatial connectivity in this data, then maybe we can actually derive some understanding from this information here. How can we summarize all of those interpolations, all that interpolation nonsense? Given the spatial relationships between different points or different parts of a data sample, we can interpolate or estimate or calculate, or whatever word you want to fill in there, the values between those points with different mathematical processes, and each of those processes having different strengths and weaknesses. The choice of which depends on data, depends on your data, your understanding of the data, your understanding of the process, your understanding of how the data was sampled, your understanding of how the data was created, so on and so on and so on. And also, from an analyst perspective, your own work in trying to find the literature or the best practices into what to use and how to show. Certainly for precipitation, there are interpolation methods. For elevation, for so on and so on. But at the end of the day, data is the winner. Why interpolate when you can sample? Well, because sampling's expensive, but do what you can.